Welcome everybody to lecture 12. This time we'll try to connect the wisdom we have acquired on special theory of relativity. Connect that wisdom with the geometry of space-time in the proper sense. As a prototype, we are using transformation from frame S to frame S prime. As a result, spatial coordinates, for example, X changes and so does the time coordinate t, xt to x prime t prime. So in a sense, it is natural to think that now we can think of four-dimensional spaces, x, y, z, and t, consisting of not only the three spatial coordinates, but also the time coordinates t. And just like we can change axis from one system of coordinates to another, now we can have similar transformations when we think of the prescribed Lorentz transformations, where not only the axis of coordinates, spatial coordinates, but also the time axis gets changed. This is the whole idea of going from a three-dimensional space to a four-dimensional space-time continuum, and that is what we will discuss. Of course, we have to realize what the exact requirements of such transformations are, given the fact that xt to x prime t prime are bound by the diktats of the Lorentz transformation equations. Just to keep it in mind, there is nothing very special in it. Look at the bottom of page 62, where in two-dimensional space xy to x prime y prime is done with the help of very well-known orthogonal transformations driven by the transformation matrix R, which R dagger R, for which R dagger R equal to 1, or more precisely R transpose R in this particular case equal to 1. Since cos square theta plus sin square theta is equal to 1, theta being the angle of rotation. This leads to the consequence that the length of, in this two-dimensional space, of length of a vector remains constant. X squared plus y squared is equal to x prime squared plus y prime squared, where x prime and y prime are coordinates in the transformed system. Now, this is a characteristic of rotation in Euclidean space, where Euclidean geometry, more precisely the theorem of Pythagoras, tells us that lengths are unchanged. However, in Lorentz transformation, we have different sets of equations given in equation 123, and t can be replaced as ct because then x, y, z, and ct have the same dimensions, and with t replaced by ct, the transformation equations also can be written accordingly. Now, I set it as a homework problem. It is written as an exercise, but the double line on the left is not very obvious. But I emphasize that this is an assignment where I ask you to do a straightforward calculation out of 123 to show that with the origin at t, x, y, and z 0, and t prime, x prime, y prime, z prime also 0, c squared t squared minus x squared minus y squared minus z squared is a constant quantity. It is a straightforward calculation, and I ask you to do this as an assignment. Now, the crucial difference with the usual invariant length is this. Here, normally in Euclidean space comprising x, y, z, and t, you would have expected c squared, t squared, plus x squared, plus y squared, plus z squared would be constant in the rotation thing. But here you have a relative minus sign between the position coordinate and the time coordinate. We have adopted a particular convention. We could have taken the other minus thing also as constant, but this is a practice we will stick to. So c squared t squared minus x squared minus y squared is invariant. And now you see, with this in mind, if you give a further spatial rotation in the xyz system, that will keep x squared plus y squared plus z squared invariant, and therefore the Lorentz transformation invariance would not be affected. That's why when we are taking all sample Lorentz transformations in the x direction, it really doesn't hurt the generality. If it is along any other direction, you can appropriately rotate the axis to make it a transformation along x-axis and revert back to the original system by rotating the coordinates where the length will be constant. This x, y, z and ct, or rather ct, x, y, z space is a four-dimensional space, but it is not exactly Euclidean space. It is called a pseudo-Euclidean space because of the property of the transformation. And pseudo-Euclidean space is also called Minkowski space because it came after the proposal. We are using it in a slightly modified way after the proposal of one of Einstein's teacher called Minkowski. Now, a vector in the Minkowski space is called a four vector. Remember, there in length definition, there will be a minus sign between the spatial and the time coordinates. The time coordinate is sometimes called x naught, which is c times t. X naught squared minus x1 squared minus x2 squared minus x3 squared is constant under Lorentz transformation. So basically, one frame or an inertial frame is just one system of coordinates in Minkowski space, and a Lorentz transformation basically means changing over from one set of coordinates in Minkowski space to another set of coordinates, where the time part, the time axis has a non-trivial shift or rotation as well. If the time axis is non-trivial, that is to say, with t-axis constant, x, y, z coordinates are rotated, just visualize that, you cannot picturize that, think in your mind, that will be a rotation purely in space. So spatial rotation is a subset of the set of transformations in Minkowski space. The most general thing will be everything is changing, and when time is not changing, time axis is held constant. It is a subclass of rotations leading to spatial rotations. Now, where time is changing, a non-trivial Lorentz transformation is called a boost, Lorentz boost as well, which is distinguished from spatial rotation pure. Now there are diagrams. Think of this xt diagram and think of two events. An event is characterized by a point in space-time coordinates where x, y, z and t or ct are specified. Think of the diagram in page 65, middle left side, where x and t axes are shown as in the figure. Consider 2 points. O is the origin. That means 0, 0, 0, 0. That characterizes an event that takes place at the coordinates 0, 0, 0 at time 0. P is another point, which I have not specified here. P is equal to CTXYZ. That is to say, another event taking place at coordinates x, y, z and time t. Now, where can P be to be causally connected with O is what we'll examine next. There is a shaded region classified or rather outlined by x equal to ct, this line. Obviously, if the point pt is within the shaded region, c squared t squared minus x squared is greater than 0, as you can see easily, which means a signal traveling from O to P, that's to say 0, 0, 0, 0 to ct x, y, z, will travel with a speed less than speed of light. That is, a signal can travel from one point to another physically. As a consequence, O and P constitute an interval not only of space but also of time, which is called a time-like interval, and the two events can have a causal connection because a signal can travel from one point to another. On the contrary, if you come to equation 60, page 66, and look at equation 127, that characterizes a point P which lies outside that shaded region. This shaded region is marked by what is called the light cone. And if P is outside it, you can immediately see that for the coordinates corresponding to P, C squared T squared minus X squared is less than 0. And therefore, the time required at the origin for an event at the origin to send a signal, or rather the speed required of a signal to travel from an event at the origin to an event at the P in this case is greater than C, which means no signal can travel and causally affect events at P if the first cause lies at O. So this is called a space-like interval, O and P, an interval where you need to have a signal traveling faster than light in order to connect them, and therefore the two events at these 2 points can't be causally connected. If P lies on the conical border of the two regions on the light cone, then of course the c squared t squared equal to x squared, and a signal can travel with the speed of c from O to P, and therefore the light is the only, or as of now, a photon is the only particle that can send a signal or carry a signal from one point to another. So this kind of an interval is called a light-like interval or a null interval. Now, all points within the shaded region, in this case, are causally connected with O. All points outside it are acausal with O. There cannot be a signal connecting them, so they cannot affect one another in terms of physics laws. And of course, this light-like surface or cone or whatever you call it, it's actually a line in two-dimensional space, but remembering that other other coordinates are there, it's called a coordinate system or a cone, a light-like cone. There along the light-like cone, signal can travel, but always with the speed c, not slower than that. So among the known signal carriers, light is the only one. This is where we end, and please carry out the exercise where the double line was missing, but where what I have written as x, showing that c squared t squared minus x squared minus y squared minus z squared is unchanged when you go from one coordinate system to another, because that is the result on which our main conclusions and main formulation is based. So this is where we end, and in the next lecture, we'll take up further consequence of such things. Thank you very much.